Alrighty, so we have in front of us here our periodic table, right? So the periodic table was made by a couple of scientists. One of them was Dmitry Mendeleev, right? And Julian Lothar Meyer. These two scientists, they decided to take all the elements that existed in nature and they arrange them in their arrangement of increasing atomic number. So they basically arranged our periodic table based on how big the atomic numbers of the elements was, starting from the smallest, working the way up to the biggest atomic number. All right. So you would see that, we start off with hydrogen being 1, which is here, helium being 2, then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, and so on and so forth. So we're going like this, right? So we started from here and we went from left to right, and that's how the elements were initially arranged, right? After some time, they did some more review, they did some testing of the elements, and then they found out the properties of the elements. Now, this table is actually divided into 2 parts. You have these columns, as you can see here. These columns that are in front of us, right? Are you all seeing the columns? So we have group 1. Let me zoom in a little more. Just give me a minute, right? All right, so we have here group 1, group 2. We have group 3, 4, 5, 6, 7, and group 0, which is also known as group 8 in certain periodic tables, right? So like I said, these columns, vertical columns, these are your groups on your periodic table. If you're going across the periodic table, you find these rows, these horizontal rows. These are what we call our periods. So we have period 1, period 2, 3, 4, 5, 6, 7. So depending on where your element falls in, there are different characteristics for the elements present. Are we understanding that there so far? Nice, everyone. So I used to always tell class from before, if it is your understanding, press 1 for yes and 2 for no. But good. Now, when you look at these elements, right? And they started, when they're testing, they started experimenting with them. They also decided that, hey, here it is now. I could actually categorize these elements according to certain properties, right? So they could do it based on ionization energy. So let me write that word on the screen. Ionization energy. Right. Now the name a little self-explanatory. It's the ability of that particular element to become an ion, right? So this is where the element will actually lose an electron or 2 to be able to become a positive ion, all right? We could also classify it based on electronegativity. Electronegativity is the ability of that particular atom of the element to form negative ions. So ionization energy dealing with positive ions, electronegativity dealing with negative ions. They also classify the elements on the periodic table based on their atomic radius, how big the atom is, and other physical properties such as melting, boiling points, and even if they could conduct electricity or if they can't. All right. So we're going to take a little look at the periods and also their reactivity, how fast they could react, right? They also classify them based on such. So the periods, like I was telling you, those are your horizontal rows of elements. So you have 7 of them numbered from 1 to 7. All elements in one period actually have the same number of electron shells. And the period number could tell you that. So let's say, for instance, we have elements that fall into period 1. We have hydrogen and we have helium. Let me say I want to draw the atomic structure of hydrogen. Hydrogen, when you have 1 electron in it, it belongs to period 1. It has 1 electron shell, which corresponds with the period number. Let me look at helium. I'm going to draw helium on the next slide. According to helium, it has 2 electrons as the atomic number, 2 electrons. Helium also belongs to period 1, so it only has 1 electron shell. You all hearing me? Let me know if you're hearing me. Let me know if you're understanding, please. All right.
Yes, miss.
Nice. So let's look at some elements in period 2. So we could look at comparing lithium and beryllium. So we're going to draw lithium here. So we put the P and the N in the center to represent our protons and neutrons as our nucleus. Draw the first circle. So lithium has 3 electrons. 1, 2. Need to go over to the next shell. 3. So lithium belongs to period 2, which indicates I'm going to have 2 electron shells, right? Now let's draw beryllium. So beryllium, draw the P and the N in the center. Beryllium has 4 electrons. And again, it has 2 electron shells. So for exams, when they're asking you to draw the electron configuration or this or that, and they're telling you use the outer shell alone, the period number can actually indicate to you how much shells you're going to have to draw. It's like a little key that you have, right, to be able to use, right? So if you're drawing electrons in period 3, right, atoms for period 3, you're going to have 3 shells that you're going to have to draw. Anything in period 4, you're going to have 4 electron shells to draw with your electrons. Anything in period 5, you're going to have 5 electron shells to draw. If you're drawing in 6, you're going to have 6 electron shells. If you're drawing any atoms from 7, you're going to have 7 electron shells. Going across the period now, right? Each atom, right, gains 1 more electron. So for instance, in hydrogen, I start off with 1. But then in helium, I have 2 electrons there. If I move over to lithium, I'm going to have 3. So when you're going across the period from left to right, the size of the atom increases by 1 more electron, right? Also, what is important to remember, so if 1 more electron is added on, 1 more proton is added on as well. What is very important to remember as well, when you're going from left to right on the periodic table, your atoms start off as metals here. But as you go across the periodic table, it's actually going to get like a non-metal. So when you're going across the periodic table, your elements go from metallic to more non-metallic. This here in the center, that is your transition metals. They're in between, right? So in some cases, they could act as metals. In some cases, they could act as non-metals, all right? Anybody has any questions there so far, or everybody good with that? All right, so I hear from Raven. Raven says he's fine. Anybody else? Everybody else good? No questions?
No questions, miss.
All right. So we're going to look at now our groupings. All right. So the vertical columns, right? They as well, just like how your periods had their own different properties to follow and different ways in which your atoms would have been arranged. Your groups, they are the vertical columns of the elements. They start off from group 1 and they go all the way up to group 8, right? The last grouping, which is group 8, which is seen as group 0 here, some books have it as group 8, some of them have it as 0, right? And I'll explain further down the line why. Now, each element in a group have the same number of electrons in the outer shell from groups 1 to 7, right? Now, if I go on a draw, let me say lithium. Lithium belongs to group 1, right? So let me draw lithium. Lithium have 1, 2, 3 electrons, right? In this outer shell here, there is 1 electron, which corresponds with the group number, group 1. Let's draw sodium. So sodium is lithium, right? Let's draw sodium. P and the N in the center, sodium actually has 11 electrons. So I'm drawing. All right, so this is going to be 10, last shell here, right? This outer shell only has 1 electron, which corresponds with the group number, which is 1. So in exams, when they want you to draw certain things and they only tell you the group number, and tell you use the outer shell alone to draw the number of electrons that will be present in sodium, you could just look at the group number. So all the elements in group 1 has 1 electron in the outer shell. All the elements in group 2 has 2 electrons in the outer shell. All the elements in group 3, when you draw it out, has 3 electrons in the outer shell. In group 4, you have 4, 5, you have 5, 6, you have 6, 7, you have 7. Now with group 0, right? When you draw the last shell, you're going to actually end up with 8 electrons in the outer shell. All right? So that's why some books have it as 8. The reason why the name is given as 0 is because when you draw out these elements in particular, the whole electron shell filled. So because the whole shell, all of the shells are filled, them can't react with nobody, right? Instead, these elements here, helium, neon, argon, krypton, xenon, and radon, they all stay by themselves. They can't react with nobody because their electron shells have no space to react with nobody. So because them have no space, them can't bond onto nobody to form no compound. So them just be chilling out by themselves. So that's why we named it as in some books as group 0. Them can't react, so put a 0 there. Them are reacting, right? From groups 1 to 7, it shows you how much electrons you have on your outer shell to know how much space you have to add on electrons in the event you have to bond onto another element. Are you all understanding me so far? Nice, good. Right. So there is another term that you're going to learn in chemistry called the common oxidation state or the common oxidation number. Anytime you hear this word called oxidation, oxidation basically dealing with how much your element, how much of your electrons an element could lose or gain to form a stable compound. All right. Now, for the elements in groups 1, 2, 3, 4, the oxidation number is the same thing as the group number. But you see, from the time you go from 5 up until 7, in order to find out that oxidation number, you take the group number. So let me say you're looking at 5. So you take the group number, which is 5, and you minus it by 8, and you get minus 3. For 6, you take the group number, which is 6, you minus it by 8, you get minus 2. And for 7, you minus it by 8, and you get negative 1. 0 had no oxidation state, because like I said, them are bonding with nobody. Group 1 to group 4, the oxidation number and the group number is the same thing. And all you really need to know is the group number, the correspondence, because sometimes I could ask you, I could probably say, hey, Kian, right? Tell me what is the oxidation number for carbon. You just have to look at the group number. Me, I give you nothing to work out, but you can look at the group number, see where carbon located and say, Miss, is group 4. If I say, well, Raven, tell me the oxidation number of oxygen. You could take the group number for oxygen, which is 6, minus it by 8, and come back and tell me, Miss, is negative 1. These are little things that your teachers are supposed to teach you in school, because for exams, you had to look at the periodic table that they give you and figure out these little itty-bitty things, right? So these are little keys that are going to help you when you get a past paper question and you feel like you're missing information. These are the hidden keys that you have to use in order to figure out your questions. Now, going down a group, the atom that get bigger by 1 electron shell. Like for instance, in lithium, it gonna have 2 electron shells. But if I draw sodium, it gonna have 3. And then potassium gonna have 4, right? And rubidium gonna have 5. And going down, it just increases. So going down a group, your atom gets bigger by your 1 electron shell. All right? Anybody has any questions there so far?
No, miss.
All righty then. Nice. Anybody in the same grouping, any element in the same group will have similar chemical properties. So you, let me say we react lithium with, let me say, acid. You're expecting sodium to react in the same manner as well, because they're similar, because they're belonging to the same group. If I take chlorine and I react it with, let's say, oxygen to create our oxide, right? I'm expecting bromine to do the same thing like chlorine because they belong to the same group. So they have similar chemical properties. So their reactions are also going to be similar. Element gets more metallic going down a group, right? The reactivity of metals, and hear me clearly, metals get more reactive going down a group because of its size. Non-metals, which are on this left-hand side of the period, on this side of the periodic table, right? Your right-hand side, sorry, this is your left, this is your right. On your right-hand side of the periodic table here, all right? Your non-metals, as they get smaller, the size of the atom gets smaller. So when you go up the group, when you get smaller in a non-metal, they are more volatile. When you get bigger in a non-metal, they are the ones that are more reactive. All right. Like I was saying, this little block here in the center, these are your transition metals. They will have 2 electrons in their outer shell, and they will have different oxidation state because they have the ability to react like a metal or a non-metal based on the situation that they are subjected to. All right. So these are just some common information, general information that you need to know for your periodic table, right? There are 2 groups that we have to single out to look at for exams, which are the group 2 elements, the group 7 elements, and we also have to single out as well the trends that will actually follow in in period 3. All right, and all the past paper questions that you will get for periodic table are actually based on that. So that's why we are singling out these to look at. So I believe with the time that we have for today, we would be able to finish this topic so that next week we could do past paper questions based on the periodic table. All right. So here's what we're going to do. At this point, we're going to restart the meeting. We're looking at our trends in group 2. All right. Now, the elements that they have here listed for you guys are beryllium, magnesium, calcium, strontium, and barium. So they're using arrows to indicate if it is increasing or decreasing, right? So for melting point, the arrow facing upwards. So the melting point increases up the group. That has to do with the size of the atom. The bigger the atom is, the harder it is to melt it. The smaller the atom is, easier it is to melt. Ease of ionization, dealing with how easy it could become a positive ion. As it gets bigger, right, the ease of ionization increases down the group. So beryllium finds a hard time forming an ion, whereas barium, as it's lower in the group, it could form an ion easier. Strength as a reducing agent. This is where it would pull out electrons from another compound, right, or another element. It increases down the group as well, right, because the easier it is to form an ion, the stronger it is as a reducing agent. If it had to react with water, oxygen, dilute acids, that as well, as the atom gets bigger, right, it's easier to react, right, or the reactivity is increased as the atom is bigger. Displacement, right, an element is displaced from a compound by an element below it in the group because it has to be more reactive. So like say for instance, I have magnesium reacting with beryllium chloride. This is displacement deals with kicking an element out. Magnesium is lower than beryllium on the periodic table, making magnesium more reactive than beryllium. And as a result, it kicks it out of the compound to give you magnesium chloride and beryllium by itself. So once it is the atom, the element is below the other one in the reactivity series, right, or this particular group, it could kick it out. But you can't say, well, all right, let me redo this one. You can't say, well, all right, magnesium is going to react with calcium chloride. Magnesium can't do that. Magnesium can't kick out calcium because you know why? Magnesium is above calcium in the group. So as a result, it can't kick it out. So reactivity increases down the group. The compounds, when it is the elements go down the group, they form more stable compounds. Basic strength of the oxide. So when these metals react with an oxide, it forms a base. So the strength of the oxides increase down the group because of the stability of the compound. Hydroxide, if it is a reactant with a little bit of water, the oxide, if you dissolve it in water, it forms a hydroxide. That increases down the group as well, strength-wise. With regards to carbonate, these on top are more soluble than these underneath, right? I mean, that it could dissolve in water easier. Anybody have any questions? Are we all right with that so far?
You got it with MS.
Nice. All right. So we're taking this down, right? Group 7. So in front of you in this table, this is the group 7 elements. This is your halogens. And I have the physical properties listed, how well they become an ion. Non-metals, which are like the elements that falls in groups 3 all the way to group 8, they typically act as oxidizing agents. These are the ones that will cause an increase in oxidation number. A reducing agent causes a loss, right? You have your reactivity and also displacement, meaning how well they could kick out each other compound. All right. So the elements that we look at in group 7, right? We have fluorine, chlorine, bromine, and iodine. It's important to know their physical properties because you may have to compare it in one of these questions. So for example, fluorine is a pale yellow gas. Chlorine is a yellow-green gas. Bromine is a reddish-brown liquid. And iodine is a gray-black solid, right? Iodine can also be in a liquid form as well, okay? It's typically a gray-black solid, right? Melting and boiling points. So you're seeing that the arrow is facing downwards. Now, when the arrow is facing downwards, it means that it's decreasing. So with regards to melting and boiling points, right? So the arrow shows an increase, in properties, right? So this means that on top here, to melt or to boil it, it's easier than down here. It has to do with the size. The bigger that the particular structure gets, the more energy it's gonna require to be able to melt it or to boil it. So for a gas, it's really easy to do. But as you go down the group, it gets more difficult. So the arrows show an increase in the properties. The density also decreases down the group. It has to do with the size. All right. With regards to ease of ionization, the smaller the atom is, the easier it is to gain an electron to become a negative ion. Metals become positive ions, non-metals become negative ions. So as you go up the group, right? When you're going up the group, the atoms get smaller. Fluorine is much smaller in comparison to iodine. Fluorine will become an ion faster than iodine because of the size of the atom or the diameter of the atom. And because of that, right, and the atom being smaller, making it easier to become an ion, the strength of the oxidizing agents, the ones higher up in the group, fluorine and chlorine, are much stronger oxidizing agents in comparison to bromine and iodine because of the fact that A, it becomes an ion easier, so it's going to actually oxidize, remove electrons from other compounds easier. We understanding that so far?
Yes, miss.
All right. Sham, you all right with that? Dominic, Joshua, Kelly and Kian? Let me know, right? Again, with the size of the atom, the smaller ones is react faster than the bigger ones, right? Nice. And displacement. With regards to the reactivity, if the reactivity, the atoms on top, because they're smaller, they react faster. That means they can kick out each other from a compound, and I'm going to show you. Let me show you a proper demonstration with this, right? Let me say we have fluorine. I'll change the color. Fluorine added on to MgCl2, which is magnesium chloride. Because fluorine falls higher than chlorine in the group, fluorine is going to kick out that chlorine very easily. Going to kick out that null for now, right? Because the smaller the atom is, the more reactive it's going to get. So you're going to end up with MgF2 add on to Cl2. Also, please remember for the elements in this grouping, fluorine, chlorine, bromine, and iodine, they exist as diatomic, right? Diatomic molecules, right? Diatomic means it has two atoms of the element that makes up that particular compound. So fluorine in compounds is represented as F2, chlorine in compounds is Cl2, bromine is Br2, iodine would be I2. All right, I'm gonna go to another one. Show you our next one. Let's see, we have, right now, but when they by the sulfur equations, they're gonna be represented with the 2 underneath. It's a diatomic. It has to be diatomic to exist by itself in nature. All right. So let me say we have sodium bromide added on to chlorine. Chlorine by itself will be represented with Cl2. Because Cl is higher than the bromine in the reactivity series, it's going to kick it out because your elements, right, because the chlorine is higher than the Br, it's more reactive. So as a result, you're going to get NaCl plus Br2. Any questions there? Alrighty. So we're taking this down, and then from there, we're going to move on to the trends in period 3. So let me know when you are finished with this. Right, so in front of us, I have a table that shows you all the elements in period 3. So you have sodium, which is Na, Mg is magnesium, Al is aluminum, Si is silicon, P is phosphorus, S is sulfur, Cl is chlorine, and Ar is argon. So the first property that they're looking at here is the metallic nature. Now your arrows show you increase of your property, right? So let me just get up inside here a little more. Right, so we're looking at the metallic nature. So if you look at it, it's from right to left, it gets more metallic, right? So that means, let me just zoom out a little bit. Zoom out. Right. So it means that from here, right, your argon, your chlorine, your silicon, your phosphorus, these are more on the non-metal aspect of things, right? Here, your sulfur, sorry, your silicon here, right? So this is a non-metal, this is a non-metal, this is a non-metal, this is a non-metal. And as you go in across like this, you start to get more metallic. So your sodium, your magnesium, your aluminum, and even the silicon has a certain level of metallic nature. From P go back to Ar, it's non-metal. When you're going from left to right, it gets more non-metallic. So here you have more metals, here you have more non-metals. Your metals are the one that will be good conductors of electricity. I am sure you get electrocuted from a plug already. Everybody does get that little jolt of electricity to them. It is a normal thing in this happen. It's because inside of your wires, there are metal contacts that will conduct the electricity. So metals are typically good conductors of electricity. Silicon is a semiconductor, it's in between. Non-metals are non-conductors. For ease of ionization for metals, right? This direction, once you have a little bit of electrons to lose, it's easier to become an ion faster for a metal. Like for instance, sodium only have 1 electron to lose. Magnesium has 2. Aluminum has 3. These here that have more than 1 electron to lose requires more energy. So it's easier for somebody who has 1 electron to give up to become a metal ion faster than if it is you have more. So when it is your valency, which is the number of electrons that you have, once your valency is little bit, the ease of ionization increases. So sodium could become an ion faster than aluminum. In this direction, the less electrons you have to gain, the easier it is to form an anion. This one in the end here doesn't even become an ion. Because you know why? All the shells in Ar, it's already completely filled. So Ar doesn't become an ion. All right? Reactivity depends on the ease of ionization. Again, reactivity depends on the ease of ionization. Strength as an oxidizing agent and reducing agent. Metals are typically reducing agent. The easier it is to become an ion, the stronger it is to become a reducing agent. Oxidizing agents, non-metals are typically oxidizing agents. The easier it is for a non-metal to become an ion, the easier it is to become an oxidizing agent. Ar ain't reacting, it has no space on the shell, them full up, them have no time with nobody. Typical formula of oxides, you have Na2, MgO, AlO2, Al2O3, SiO2. You have 2 oxides here for phosphorus, 2 oxides here for sulfur, 1 chlorine oxide, argon in hand. Argon likes to be by itself. Bonding and structure of the oxides, right? So this is the type of bonding that occurs. Metals typically form giant ionic lattices. So they have ionic bonds. Al will have some ionic with some covalent. From here goes back, covalent molecules. Nature of the oxide, this is the pH. If it's acidic or basic, basic means alkaline. Metals are basic. Amphoteric means that they're in between, right? So aluminum in between. And the rest here is acidic. You have the different formulas of the chlorides here listed as well. And it's like what type of bonding it will occur between the elements to form that chloride. If it's an ionic bond or if it's a covalent bond, which we'll be looking at further on in the chapter. You just need to know the classification. All right. Does anybody have any questions based on the properties? All right. So we're going to attempt a past paper question now based on the periodic table. So let's zoom in up a little bit. Could you all see clearly here?
Yeah, miss.
All right. So this is out of June 2013. All right. So just centering it back. Figure 2 shows a section of a periodic table with two unknown elements represented as X and Y. Use the figure to answer the questions that follow. So they give you a periodic table here, well, part of a periodic table, right? In this part, they give you the elements, sodium and magnesium. So that group 1 and group 2. Remember the center there, which they didn't put any elements for, that is your transition. Aluminum belongs to group 3. So then they have silicon 4, phosphorus 5, sulfur 6, chlorine 7, and argon is 8. So those are group numbers, right? So they just give you a 1 element from each one of the group in there, right? And while you have X and Y, they didn't identify what the elements was, but they have them in the group, all right? So for 2A, they ask you all to compare Mg and X in terms of ease of ionization, and Cl and Y in terms of the strength of oxidizing power. Provide a suitable explanation for your answer in each case, right? So the first thing that you have to do for this question, right? So let me take the one with Mg and X, right? What I want you to do is to identify the group that Mg and X belongs to. That's group 2, right? From the time you see magnesium, you're supposed to click in your head A. Magnesium belongs to group 2. So whatever element X is, it belongs into group 2. So once you know what group it belongs to, right, you could go back into your note now for trends in group 2. And I want you to compare the ease of ionization. So you go onto the table that you have there in your notes for ease of ionization for trends in group 2. And it reads, as the diameter of the atom increases, the more easily it loses valence electrons to form ions. So, and the arrow was pointing downwards. So that's supposed to indicate to me that A, X is lower than Mg on the grouping. So your answer, when you're answering these questions, is always important. This is something you should have learned in primary school. You take a part of the question to start off how to answer, right? So you could turn around and say, X becomes an ion easier than Mg. They wanted to know which one becoming easier. So you compare it, right? And then you explain why. And the explanation is given in the table. They want you to do the same as well for the comparison between Cl and Y according to the strength of the oxidizing power. So for that first part, you're stating which one going to have a stronger oxidizing power. So for each time you identify that A, Cl belongs to group 7, you go to trends in group 7 because Y in that same group in 2. You go across the strength as oxidizing agent. You would notice on your table for that in that one for trends in group 7, as you go up the group, it becomes the stronger the oxidizing agent, right? So you could turn around and say, well, Cl will become will have a stronger oxidizing power compared to Y. And then you explain, which the explanation is there stated next to it. You all understand what you have to do here? Think you understand how to answer the question?
Yeah.
Right, so these were your answers here. Here's the next part now. So they want you to state one physical property that is similar between X and Y, and one that is different. So physical means what you could see physically, right? So let's look at X and Y. Let me go back to X and Y. Right. My advice, you're all home and you're doing this. So you go on to your normal periodic table and you determine what element X is and what element Y is. All right. So typically these two, they will actually be solids, right? That is a physical property that they will have. They are solid. But differences is one is on the metal side and one is a non-metal. So you could use that there to help you out. And I see the other part. Element Y will bond with phosphorus to form a compound. State the type of bonding that occurs between phosphorus and element Y. Right, phosphorus. Right. So anytime a non-metal, which is like phosphorus, sulfur, chlorine, etc., and anything that falling in those groups, anytime a non-metal reacting with a non-metal is going to give you something called a covalent bond. All right. So that would help you out with that answer. You get a covalent bond between two non-metals, right? It was listed there in your bonding structures. Take a couple of minutes, complete it. When you're finished, we'll correct it together.